Hi everyone, I'm Ajula Gupta. I am a technical associate at IIHS under Sustainable Energy Lab, and I will be the moderator for today's webinar on calibrated model on experimental building to test passive thermal comfort solution. This is the third webinar for the Net Zero Building Fundamental course on Coursera. Now, we have the speaker Amanda Thornau-Jam, a senior technical associate under same Sustainable Energy Lab at IIHS. She conducts research that integrates passive approaches with the IoT-based controls, working in the areas of thermal comfort, affordable cooling, visual comfort, net zero energy and water design, sustainable dashboards, and calibrated simulations. At IIHS, Amanda manages Solar Decathlon India, the largest net zero building challenge in the world. Amanda is also full-time faculty for the Urban Fellowship Program at IIHS. Amanda works on performance monitoring and designs passive strategies for the new campus to create energy efficient, climate responsive spaces. So, yeah, over to you, Amanda. The presentation will be for 45 minutes. The last 15 minutes will be for question answers. Yeah, over to you.
Um, cool. So thank you, Arjita. Thank you for the introduction. Hi, everyone. Good afternoon. Thank you once again for joining today's webinar. Um, I know that some of you have gone through the Coursera course. Some of you have not gone through the course. However, this webinar, which I'm going to cover today, is mostly about calibrated model and also passive solutions and how using energy simulation, how we could make important decisions for a case study that I will talk about today. That is it possible to create buildings that are not just cost effective, right, but also thermally comfortable and also something which is future ready. um, I know that sometimes this sounds like a dream, right? But here is the good news that it is totally possible. All it takes is some of your smart passive design strategies, and clever building energy simulations, and also a bit of future focused thinking. And for each of these three things, I will tell you more about what it means. So now, if you're new to what building energy simulations are, let me break down a bit for you guys, if some of you are new to this term. So building energy simulation is nothing but it's like creating a virtual version of your building design, so that you can, check how your building design would perform in terms of energy or any other performance, right? It could also predict how it will behave when it is actually built. So this is something cool, right? If you haven't heard of this before. But today, what I'm going to cover is slightly one step further, right? Which is using a calibrated simulation model, so that you can test how your building performs under different situations, your existing building, right? So I will be sharing some story of an experimental building which is built in Bangalore. This building has been designed with passive features like insulated walls, natural ventilation, and some of the eco-friendly materials that were used. Um, Now, this experimental building is part of a massive 55-acre campus, which is being planned for as a future ready buildings that will come up inside this campus, right? So let's get into some of the key statistics before I dive into the detail of calibrated model and its performance, etc. So we all know that buildings are responsible for about 38% of global CO2 emissions, and in India, that number is around 24%, which is again a huge share of the pie, right? And to tackle this, we have set some ambitious goals, that by 2030, we need to cut direct CO2 emissions in half. And why is this? Because that's our roadmap to achieving net zero carbon building sector by 2050, right? That is being planned. Now, who is responsible for making this happen is it's us, right? As designers, as builders, as innovators, we have an opportunity to decarbonize the building sector and contribute to the global target for sustainable future. But here is the thing, it's not just about cutting emissions, it's also about making our buildings more comfortable and something where people can live, right? So, and by using passive design solutions, we can reduce emissions and improve the quality of life. That is why it is important that you evaluate your passive design strategies and understand how they would impact thermal comfort inside the building. Because at the end of the day, sustainability is, all about where we live and the people, right? So before I start, I want to start with a story of the experimental building. And this revolves around this, the whole webinar will revolve around this building. So this building is actually was actually built as a prototype to test different technologies and also operational strategies for all the campuses that would come up in the 55-acre campus, right? But here's the thing, this building was designed with insulated walls. All the walls in the experimental building are all insulated. We use materials like CSCB, ramp earth, and AC blocks with XPS insulation in all the walls. Now, this building is also being heavily monitored to measure things like, indoor environmental quality, which includes temperature, RH, air quality inside the building, and also some of the outdoor parameters where we have weather station that is installed. So we're looking at water performance and also energy performance to understand how it would behave, right, in the experimental building. So it's heavily monitored. And this building is about 450 meters square. And again, like I mentioned, it uses different passive techniques and materials, etc. The idea of the experimental building was that we want to use this building as a tool to refine other buildings that would come up in the entire campus. Now, the interesting part is that we have all this data that we have monitored about how insulated walls would perform. But the question was, what if we did not use insulation, right? How would the building perform then? Would we save cost, and even if we save cost, would it still give good performance, etc.? This was some question that had, in many of our minds. Unfortunately, we did not have any non-insulated case to compare the measured or the monitored data since all the walls were already insulated. But why is it a big deal? It's because why this question is a big deal is because the cost of insulating the entire campus was estimated around 30 crore in INR. And also, plus, let's not forget about the maintenance cost that would come with it. So, and also another question was, in a climate like Bangalore, do you really require, insulated wall, etc.? These were some questions that always were floating around, right? So that's why we decided to dig deeper into a detailed cost benefit analysis to figure out if it's really investment worthy or not, right? Um, so we decided to address this issue through a calibrated model. And I will talk more in detail about what calibrated model means, right? Um, so here's the main objective. The objective was very simple, that using calibrated model, we want to assess the difference in the value of insulation between the present and future weather scenarios. Like obviously, we also want to look at insulated and non-insulated wall. So there are two things, two objectives to determine the value of insulation in terms of thermal comfort that it provides. And the second one is to assess cost effectiveness and thermal comfort between the present and future scenario. And the methodology that we followed was that we started with a detailed energy audit of the building because we need all the data of how the building is being performed, right? Then we model a calibrated energy model. Then we looked at the typical meteorological weather and also looked at future weather, how it will perform. And for each weather, what we did is we looked at what is the life cycle cost and also the thermal comfort that it would provide. Now, let's break down a bit more about what a calibrated model is and how we should approach it, right? So, when we run energy simulations, you might wonder, right? How can I be so sure that this results would actually match what's going on in the real building? And that's where the calibration model comes into play. So model calibration is all about adjusting your simulation model or the simulation results so that it aligns with your real world or your monitored data of the building. And once that is done, you now have a model that can predict how your building will perform in different situations. You can use it for various case studies with a high level of accuracy, right? Now, what are the benefits of calibrated model? There are multiple benefits of calibrated model, but I'm going to talk about three things. One is more reliable predictions because it has been calibrated with the actual measured data. So they give us more accurate view of how your building's thermal performance or energy use would be. And of course, you make a smarter decisions through using calibrated model and also meaningful analysis. So calibrations takes out all a lot of guesswork, giving us results that we can really rely on to make something solid, like solid decisions. And on the methodology, here is how we went about. So how we started is that after collecting all the energy audit data and all the data of the building as it is being built, first we try to match the building geometry in the simulation model. So we started by using as-built drawings as a reference to make sure that the model is reflected as the actual building layout is. Then we looked at matching the lighting loads. So again, we used the energy audit data uh, and then gave inputs of all the lighting loads in the model. Similarly, we did a similar thing for the equipment as well. Then the fourth thing that we did is replacing so far we have been using the typical meteorological weather data. Then we replaced the TMY weather data with actual weather data. So this actual weather data, we had it because we had weather station in the campus. So we used that weather station data so that it matched the actual data as much as possible. Then the last thing that we changed in the model was tried to match was the occupancy schedule. So we collected the occupancy patterns directly from the attendance logs so that we make sure that again the model reflect the real usage schedules. Now, so once we have the calibrated model, there were two errors that we were looking at, right? So you have the model ready with all those 4 to 5 steps. Then you run simulations and we look at two errors. So one is the mean bias error and one is the RMSE, root mean squared error. So these were the two errors that we look at to see how close your model is with the real world data. Now, this two error is based on the ASHRAE guideline 14. Now, what ASHRAE guideline says is that for MBE, which is the mean bias error, your results should be within plus or minus 10%. And then for RMSE, it should be within less than 30%. But this 10% and 30% is for hourly data, hourly readings. Why I'm saying this? Because ASHRAE guideline also talks about monthly energy data. So you can either choose to calibrate your model based on your hourly measured data or your monthly energy data. But for monthly and hourly, your error range will be different. Right now, what I'm talking about is for hourly data. The reason we went ahead with hourly data is because this building was newly built that time, and we did not have energy data for full 1 year, which is 12 data points. However, we had indoor air temperature, surface temperature, which were already where we have been monitoring for more than a month or so. So we used hourly data for 1 month, which were giving us around 720 data points. So those were the early data that we used. So for our analysis, finally, we use indoor air temperature, inside surface temperature, and outside surface temperature. Now, so we then compared your simulation data and the measured data and calculated the two errors that I mentioned. And these are the results. So for RMSE, they were always below 30%. As you can see in the chart. And right now, the x-axis is all the steps that we followed, and the y-axis is the error percentage. So they were all within less than 30%. For the mean bias error, what happened is you can see the 10%, which is a red dotted line. In case of in the process of using the actual meteorological data, which is the actual weather data, we found that changing global horizontal radiation had no impact on simulation results. That was something that we found. And in terms of the steps that we followed, so we had to take after step 4, we had to take additional correction steps, and I'll talk what it means. Because even after step 4, which is after changing the actual weather file, for indoor air temperature, we did not achieve the desired error percentage, right? You can see the blue line, which is above the red dotted line. So we had to do further calibration to achieve that. Now, yeah. So initially, this is the goal that we achieved, right? The mean bias error was 9%, which is less than plus minus 10%. And then the RMSE is 17% that was achieved. But 17% was achieved through additional steps, which I'll talk about. But before that, I want to show you, talk a little bit about this graph here. You can see that the red line is the measured indoor air temperature, and the blue line is the simulated indoor air temperature. You can see there is a difference, right? At some period, as per the schedule, there is a wide difference in the temperature, which we have written here that 4 degree, during the unoccupied hours, you can observe. So what we then did is, to get the 17%, we modulated different thing in the model, like, changing window schedule, improving the insulation, or sometimes removing the insulation, etc. So in this graph, this is showing all the changes we had to do to achieve that 17%, to reduce, to get it lower than 30%. But what we realized is that to achieve that, we had to, the equipment needed to run for 60% of full load for 24/7, which is actually not true in the real scenario to match the model. Then we further investigated, what is happening inside the building. So the question that we had was, what is this constant internal load in the building that is always there, right? Then we started brainstorming, right? It could be the vampire equipment loads. Are there any rats occupying the building at night? Are there any dogs occupying at night? Or is there any heat that is leaking inside the space? So all these scenarios, we started brainstorming. And finally, what we did is we went there and then we did a thermal imaging of the whole space. But what we realize is that the measuring tool, which is the equipment that was measuring the indoor air temperature, you can see the thermal image of that. We call this the IoT box. So it was actually producing heat. So it was maintaining this constant indoor air temperature because of the heat. It was not reducing at night, which we would intentionally think, right? It would reduce at night. That's the kind of some trend line it would follow. That wasn't happening. Throughout, it was trying to maintain a very constant temperature, which is due to this heat that is generated in the measurement tool or the IoT box. Now, then the next question is which data to use for calibration. So then we said, let's look at surface temperature, because we also had surface temperature of inside and outside temperature. So let me just break down a bit on this graph here. So the dotted lines are the measured inside surface temperature, right? And the red colored line is the measured outside surface temperature. So you can look at red and blue, which is outside is red and inside is blue. And then dotted lines of red and blue, again, red is outside and red is in. So if you actually see that during the unoccupied hours, also I've marked in the chart. So the simulated outside surface temperature profile was matching the measured data for occupied and unoccupied hours. So I will show this in more further detail. So dotted line is the inside surface temperature, and the inside surface temperature is the dotted line. However, the single red line is the indoor air temperature. If you think about building science, you would imagine that the indoor surface temperature to have some time lag, right? It would lag, which means when there's a dip in the indoor air temperature, the dip in the inside surface temperature of the wall would happen slightly later, right? But you don't see that in this. So we investigated further about why this is happening, right? And this is to explain why that is happening. So the sensor that was put on the wall surface was exposed and insulated. What we realized was it was exposed and insulated, which means that more area of the sensor surface area was in contact with the air temperature, and less area was in contact with the wall, which is why it was reading very close to the indoor air temperature rather than surface temperature, right? So then we realize, oh, so does that mean our simulation results make sense, right? Because we saw some errors in the measured data. So let's look at the simulation data only. Now, all these blue lines are all the simulation results. We can see that the drop in the air temperature is observed when the outdoor air temperature drops, right? There is a time lag of about an hour, you can see, between the indoor air temperature and inside surface temperature. So thus simulation results makes more sense, right, than your measured data. So through this process, there are a couple of learnings that we have had, that, model calibration help us investigate how the building operation is happening, as well as the measurement system. So after this, we really had to change all our IoT box, which is the measuring box itself, the design of it, etc., so that it takes accurate measurements. And of course, another learning is use of building science, that first principles actually gave us confidence in the model, and we had to uncover measurement data errors because of these principles. So, but for our main objective, we still had to calibrate our model. So we did recalibration. What we did is we took another set of measurements using a calibrated measuring tools. And then this is the result we saw. We finally had a calibrated model. So here you can see that the green line is the IoT box data, which is the wrong measuring box. However, you can see that new measured data, which is the black line, and the simulated data, red line, which was very close. And this is the 17% that was achieved that I was talking about. So through another set of readings, we were able to finally calibrate the model. Now, the beauty of calibrated model is that you can do a lot of things with it once it is calibrated. But for this webinar, I'm going to talk about only one part of how we had used this model, which is looking at the life cycle costs of materials that we envision to use in future, and also how it would perform, what would be the thermal performance of these materials. So we use there are three types of materials, right? However, we finally had to simulate 8 assemblies. So each of them with insulation and without insulation. Some of them had, cladding. Some of them did not have cladding. So these were the 8 wall types that we simulated to check the LCC and also thermal comfort. For the life cycle cost analysis, we really did a very detailed life cycle cost analysis. Of course, we did not use any complicated tool or something, but we used an Excel tool. We developed an Excel tool for this study itself. We considered energy cost, and then the utility tariff. Then we look at capital cost of civil works, and also considered the cost of air conditioning. We also considered maintenance, replacement cost, um, again, project management cost, GST, all the possible costs were considered for the LCC calculation. Yeah, these are some numbers that we had used. Um, Yeah, so one thing that I want to also add is that uh, apart from with insulation and without insulation, and also historical weather file and future weather file, there were another third parameter that we also looked at, which is mix mode, between mix mode and fully air conditioned building. So when I say mix mode, if your whole building, some part of it is conditioned and part of it is not conditioned, or throughout the year some period of your building is conditioned but the remaining period you don't condition. So that is one scenario we considered. And then the other scenario is when your building is fully conditioned throughout the year. So mixed mode and air condition. Now this result is the life cycle cost for mixed mode building. Now, yeah, so you can see that the blue highlighted part is for the historical results, and the green part is the future results. And you can then see all the 8 wall systems that I mentioned before, right? So in both the cases for mixed mode, you can see that your life cycle cost increases with insulation, right? In this case, mixed mode. So what I would say is that in mixed mode operation, we did it for 50-year life cycle cost analysis. The insulated wall was not cost effective because you can see that it increases, right, in all the scenarios. And with the, it's not cost effective even with the historical weather conditions or with the future weather conditions. And this is because of the insignificant reduction in the utility cost, right? So you can see the blue color in the chart. There's minimal reduction in the mixed mode scenario. So because of that, the utility cost is so minimal compared to your capital and maintenance cost, which is why you're not seeing that it is cost effective over 50-year life cycle cost analysis. Now, the next chart that I'm showing is for fully air conditioned scenario, right? Again, you have historical weather, then you have a future weather. Here you can see that in most of the scenarios, um, forget about the last bar, which has cladding in it, right? Which has cladding in it, which is slightly very high. Again, because of the cladding cost, that is very high. But or else, if you see that the life cycle cost reduces. So here, what we are seeing is that the insulated wall is cost effective with TMY weather conditions and also future weather conditions. And again, because of the significant reduction in the utility cost compared to your mixed mode scenario. Now, so that was part of your life cycle cost analysis. So we looked at whether your cost will reduce or not, etc., etc. But the question is, how would it perform, right? Will it be thermally comfortable with insulation or without insulation? So finally, mixed mode operation, we saw that life cycle cost analysis for insulated walls are not cost effective, which means we don't want insulation if it's going to be a mixed mode operation. Again, this is to say that this is for Bangalore climate and not for all the climate. And also here in this building, it was 70% of the spaces were unconditioned, right? But the question that we wanted to answer in the next part is that are these unconditioned spaces thermally comfortable with insulation in future weather conditions? So what we are trying to say is that, okay, life cycle cost analysis said that for a mixed mode operation, you don't need insulation because it's not cost effective, right? But the question we're going to say is, okay, let's say it has insulation in them. Would it perform thermally, right? That is the question we're trying to answer. Will it be thermally comfortable? So this chart, this graph here is showing the operative temperature for non-air conditioned building, which is naturally ventilated. And this is with insulation, right? This is again for TMY, which means historical weather data. The gray band here that you see is the comfort band, right? Is the comfort band, which means that if all this operative temperature, so all these points, if it falls within this band, then you will be comfortable inside. If it falls outside, then those many hours you are not comfortable, right? That is what this graph is showing. So here what is showing is that 13% of the annual hours, which is 8760 hours, you will not be comfortable. You'll be uncomfortable. And you can also see that most of the comfortable hours are below the gray band, right? That means your building is behaving cooler, right? Again, this is with insulation, right? So if your building is insulated, what this is telling is that 13% of your annual hours, you will not be comfortable. And also it means that your building is kind of performing cooler, right? That means this is not a cooling problem and it could be easily solved by maybe closing the windows during the times when ambient temperature are particularly low, right? It is solvable. Now let's look at the future weather. What if we simulate for future weather, what does it show, right? Here, what it is showing is that 11% of your annual hours, you will not be comfortable, right? So again, this ban is for 2080 ban. The previous one that you're saying is for historical ban. You can see that even this band has moved up, right? Which is the comfort band. This is because we're assuming that we will be adapted to the warmer conditions in future, right? Now, so here it's showing 11%. So this means that the 2080 building operation um, uh, against your comfort band, NBC comfort band, it shows that for a naturally ventilated building, you will have only about 11% discomfort hours. With operative temperature going a maximum of maybe 3 degree Celsius above the upper limit of the band. Now, this third part is again your future future weather generations. However, your band is still your typical thermal comfort band, which means that we are assuming that we will not be adapted to warmer global or local temperatures in future. So in that case, our thermal comfort will band as same as it is. However, if your building is for future, how would it perform? So you see that the number of discomfort hours have increased here, right? So it's gone to 31% with operative temperature maximum of about 6 degrees Celsius above the upper limit of the band. Now, so what did the thermal comfort assessment tell us? So the thermal comfort assessment told us that if for future weather, your operative temperature, right, will exceed the upper limit by about 3 to 6 degrees Celsius. And through literature, we know that ceiling fans are able to provide about 6 degrees Celsius of corrective power, which means if you have ceiling fans turned on, you can reduce certain amount of temperature, right? And in Bangalore future climate, if we have insulation in walls, it will provide thermal comfort without AC if ceiling fans are switched on. But one question that remains is, will thermal comfort band shift upwards, assuming we will adapt to future conditions or not? If we are not able to adapt, then maybe even ceiling fans might not be possible. So finally, I think through this case study, this is the conclusion slide. I think this is my last slide. So the overall results through this study was, of course, some learnings from the calibrated model, etc., that which I talked about, but especially for the LCC study and thermal comfort study, we saw that insulated walls have a lower life cycle cost if the building is fully air conditioned, whereas in mixed mode operations, it has higher life cycle costs for insulated walls. And this is true for both historical weather and also future based analysis. And in the detailed thermal comfort analysis for historical weather and 2080 weather, we saw that insulated building is able to provide adequate thermal comfort with about 11 to 13% of discomfort hours over the annual years. And if the 2080 case does not include full adaptation of thermal comfort conditions, right, which is consistent to the adaptive comfort equation of the National Building Code, then the worst case would be that 31% of the discomfort hours will be there, right? We will not be comfortable for 31% of the annual hours, and which is about 6 degrees Celsius outside the comfort band. So I think the two big takeaways from this study is that one is that through a stakeholder discussions, using calibrated model and through this study, we decided that for the upcoming building, we do not, for a climate like Bangalore, we did not require insulation in buildings. And which is why, because of this, we were able to save 30 crores for the whole entire campus, right? And another is that another takeaway from this study is that uh, a building like this, like the experimental building that we looked at, with right decision, be with good insulation and natural ventilation, we can comfortably stay. We can stay comfortable even without air conditioning. Maybe we do not need AC even in Bangalore for many years, right? Because we looked at future weather, and maybe the only time when you require, when you need air conditioning in such building, uh, maybe ceiling fans would be more than enough, right? So I think you also saw an example of how calibrated model can do. We had other case studies where we had used calibrated model and where we were able to make right decisions using the model. And I'm sure you if you have a calibrated model or you calibrate simulation model, you will also be able to do much more decision making through the process. Yeah, so thank you.
Thank you, Amanda. Very nice presentation, and good to know that we can save 30 crores just by simulations. Good knowledge. So we have one question from Atif. That's, I hope I'm pronouncing it right. Okay. Many questions. Okay, so one is that very thorough analysis and nicely presented. When you consider future weather conditions, did you also consider future energy tariffs?
Yes, we also did consider future energy tariff. That's right. Yeah.
Okay. And we have one question from Karina. Karina, do you want to speak it or do you want to have it like through written? You can raise your hand. Okay, so her first question is, so for any project, can a calibrated model be directly created or does it require simulated model to be created first?
Okay. So for any so you will need a simulated model. However, it will not be as just a simple simulated model. Like I mentioned, you would need a lot of details of how it was actually built, how it is performing, etc. All those details would be required to calibrate your model as close as possible to the real world scenario.
Okay. Second is, what would be the requirements to create a calibrated model for a project? So yeah, as Amanda mentioned, all the specifications that is in the real world. The third is, you also mentioned that for the experimental building, there were no walls without insulation. So how did you compare the performance of insulated versus non-insulated walls?
Yeah. So so this was the main question, right? We were trying to solve. So what we did is we developed a calibrated model of the building with the insulation, right? And then once we know that this simulation model is calibrated with, whatever less percentage of 17% of MBE and 9% of RMSE, then we said, okay, this is calibrated. Now we will remove insulation and run the simulation to see the results. How would it perform? So that's how we had compared with and without insulation. Once you know that your model is calibrated.
Okay, so the next question is from Ojo. Thank you, Amanda, for an amazing presentation. Aside the noted heat source from your IoT box, how else were you able to ensure the simulation aligned with actual calibrated model? I know you mentioned the temperature sensor placement also.
Can you repeat how?
Yeah. So the question is okay, wait a minute. Aside, how else were you able to ensure the simulation aligns with the actual calibrated models? Other than the measurements, what else did you look at when you think that, okay, now calibrated is aligned to the actual model?
Yeah. Uh, yeah. So for the calibrated model, we only looked at the measured data, which is indoor air temperature, and surface temperature, which is inside and outside temperature. Based on the two data, one is your simulated data, and the another one is your measured data. And for the same timestamp, you look at what are the errors, right? That's how you calculate the MBA and RMSE. I hope that answers.
I think, yeah. I think, Ojo, can you raise your hand if it's answering your question or not? We have two people. Okay, one question. Yeah, Ojo, you can speak.
Hi, Ojo.
Hi, Amanda. Thank you very much indeed. Yeah, I think you actually answered. So my concern actually is because most times, and I dropped a follow-up question. Most times you don't have opportunity to calibrate your model. I mean, that's the majority of the cases. You only have a simulation at best, and then you want to see how you can implement that. I mean, it's costly having a test model for calibration. In your case, the finance, and it's actually for a bigger project. So, from your learning, what are the take home of what you might give as an expert advice on considerations when developing a model? The very careful considerations so that your model can perform, can play. How do I say it now? Can be optimal in real world scenario while you are not being overly conservative because you want to do, I mean, you want to deliver a green building, I mean, you want to meet up to specification, because there are a lot of factors affecting in the real world scenario. You have occupant behavior. In your own case now, you notice that your IoT box was generating some, funny signatures and
Yeah.
all of that. So, what are aside those small issues, what are the very particular considerations that we must ensure so that our simulation does not deviate substantially from real world performance?
Yeah. Thanks, Ojo. Yeah. So we took a slightly difficult pathway because we did not have energy data. What I feel is that if you would have had energy data for 1 year, right, that would be a slightly easier calibration rather than looking at hourly data. However, another issue that we also faced is through the hourly data pathway is that in terms of schedule, sometimes you're not sure how the building was performing during that period that you calibrate, right? It's especially in terms of it's a naturally ventilated building. How was the window schedule? What was the movement of people? Um, but luckily, because it was slightly planned ahead, we had detailed data. Also, we were able to do energy audit of how each equipment in the building would perform, which means we had details of what the lighting power density of each space would be, and also what would be the equipment power density of each space would be. So I think planning ahead of all the data that you would require for calibration uh, is the way to go. However, if you don't have all these details, I would suggest that you can go through the energy data pathway. If you have energy consumption data of each month for at least 1 year, you and also, of course, all the information about your building, especially your construction type, um, and some level of your load inside the building and your energy data, I think you should be able to do some calibration.
Yeah, thank you, Ojo. Now we have Kunal Khairnar. Kunal, you can ask your doubts.
Hello.
Hello, yeah, we can hear you.
Yeah, actually, I posted my question. My question was that can we calibrate the whole building with the calibrating the air conditions of any one room?
Kunal, did you say can we calibrate using air condition inside the building?
Yeah, I mean
With
the temperatures of a room. I mean, if I calibrate a room of the building in the model, can I say the whole building model is calibrated?
Okay, so yeah, I hope I understood your question correctly, but yes. So in this experimental building, we had it was a mixed mode, right? So we had spaces which were air conditioned, and we also had spaces which was not air conditioned. And we did calibrate for two kinds of spaces, right? So it is possible to calibrate for air conditioned building spaces as well.
Yeah.
No, I'm talking in the case of unavailability of the most of the data. So I want to calibrate the whole building, but I'm not able to measure all the conditions at all the points. So can I calibrate on the basis of uh, any one place?
One
Or
space.
yeah,
Yes, but you will have to model all the surrounding buildings, because that would have some impact, right? Let's say your
yeah.
your conditioned space is adjacent to a non-conditioned space, for example. So that would have an
Uh,
impact on your conditioned space. Um,
in our case, it's actually whole naturally ventilated building.
no, it was a mixed mode building, which means we had some spaces which was air conditioned.
Okay.
Yeah, so 70% of the spaces were naturally ventilated. The remaining 30% were air conditioned. So we had to model the whole building, not only one space. Yeah.
Amanda, we have one question from Elias. What were the tools used in this study?
Yeah. Oh, good question. I think I did not mention this in the start, Elias. Yeah. So I use Design Builder simulation tool to do the calibrated model. Other tools that were used were Excel for lifecycle cost analysis. Another tool I would say is the IMAC tool, which is Indian model for adaptive comfort, because I wanted to get the comfort band, right? Understand whether it is falling, you are comfortable inside the building or you are not comfortable. So we also use the IMAC comfort model. Yeah.
Okay, one more question is from Atif. Since everyone may not have the skill or capacity to do the same, how do you suggest calibrated modeling becomes the norm? Can IoT or smart metering play a role in simplifying this work?
I think that's a very good question. I do not have a direct answer, but I would like to take one example, one scenario where we were able to calibrate a model very quickly. This was one of my colleague who had a building which was just built, and then the windows were all closed, because it was of course planned before that he wants to calibrate the model of that building. The windows were all closed. There were no fans or no internal load, I would say, during that period, which means there's no internal load, there's no schedule of people, there's no schedule of windows, and he was able to calibrate it very easily, even without using the actual weather conditions. He was not able to get the because he did not have weather station in the building. um he could get weather data from the closest weather station in and around, and he was able to calibrate it very quickly and easily. So that could be one way to do it, if yeah. But I'm not sure about how using IoT or maybe like an AI thing, how this can be made like even more simpler. Another scenario could be that we also, using this calibrated model, we also did a machine learning project where we use the calibrated model to predict operative temperature for multiple buildings. But yeah, I don't think this is relevant to your question. Yeah.
Next question is from Hari Venkat. In the wall type alteration 4 that was shown, how did you model the air gap in the wall in your BPS simulation tool?
In
How
yes,
did you- yeah.
yeah, yeah. So the air gap in the design builder simulation tool, you can actually select, based on your actually built assembly, you can design your wall assembly. It will have different parameters that you can select. Through that's how you give the input. So I'm sure if you have used any other energy simulation model, this is possible. But if you haven't used, that's how you can do it. Yeah, you select those materials, including air gap, etc., with the depth of your air gap, etc.
One question is from Nishay. You mentioned that the equipment was running at 60% of full load for 24 hours by 7. How did you account for that adjustment?
Okay, so if you remember that, maybe I can show that graph. Yeah. So what we did is that, second, yeah. So we were not able to achieve the MBE. It was all slightly higher than 30%. So we had to reduce it. To reduce it, even though we have done all the adjustment that is possible with all the information that we had, it was still above the 30%, right? That means somewhere the building is not performing, your simulation model is not performing as it is. So what we did is, we said, okay, what could be the possibilities, right, to reduce this percentage, right? Reduce less than 30%. So we investigated and we saw that there's during some part of the hour, it was always higher. It had higher, air temperature. So to increase air temperature, we said, we brainstorm what can be done. Maybe remove insulation, increase internal load, etc. So all this were tried, right, to match your measured data with your simulation data, right? So through this, we realized that if we increase your internal load to 70%, then only you're able to match between your measured and simulation, right? But increasing 70% was not really true in real case scenario. Then we went ahead and then investigated what is happening inside the room, what is causing internal load, high internal load, etc. That's when we realized that your measuring box itself was always, heated up, etc.
One question, since only 31% of ours have the temperature above the maximum comfort threshold, is there any simulation run to check how much more energy is required to run fan or ACs to get the thermal comfort without insulation?
That is a very interesting question. I who Yeah, who asked this question? May I know?
Yeah, it's an anonymous attendee. It's in the
Okay,
question.
yeah. So that is a very interesting question. Of course, we haven't done that detailed analysis in terms of what kind of energy consumption would it require. Yeah, but it'll be interesting to know. Yeah.
Okay. Without the IoT box, what will be the methodology of data collection?
Okay. So we did a second round of recalibration, right? Which I mentioned. There we had used 1 week data. So we had used 1 week early data, not using IoT box, because we know that IoT box is giving wrong data. So we had used Hobo data loggers. So you can also use data loggers to log continuous data, uh, to get early data for calibration.
Yeah. And the last point is, what is the impact on foundation and structural load for building of different wall types used in modeling?
What is the impact of?
Foundation and structural load for building of different wall types used in modeling. Basically, different structural loads for different wall types.
Okay. Yeah, Yogendra, I think this is a good question. We did not assess any impact on the foundation or structural load, etc. We were only looking at impact of different wall types with insulation and without insulation. But however, in the simulation model, we did use input data of all the actual material used in your, foundation, structural, ground, etc. All those details were incorporated. Yeah.
Because he wants to know the LCC will change accordingly.
Yeah, the LCC that we had done was only for the wall assembly, not for the whole building. We were looking at only the wall assembly separately.
And I guess we'll take this as the last question. Do we have to do CFD analysis as well?
CFD, I think CFD analysis would be for a separate study. Uh, we were only looking at thermal comfort and life cycle cost. But yeah, I mean, if you are interested to understand, because it's a naturally ventilated building, it will be also interesting to know how the wind would flow and how would it impact thermal comfort, etc. But one thing to note is that we looked at operative temperature, right? We did not look at air temperature for thermal comfort assessment. So operative temperature also takes into account of air change, etc. inside the building. Yeah.
Thank you, Amanda, so much for the wonderful presentation. And for
Thank
those
you.
of you who are not familiar to Coursera, we have put the link of the Net Zero Building Fundamental course, and you can log in and you can enroll yourself for the course. Thank you so much. Bye. Have a nice
Thank you everyone. Yeah.
Yes.
Bye.